All right, let's jump right in. We're surrounded by these absolutely massive, incredible structures. Bridges, stadiums, you name it. And they all share one big secret. They're in a constant, invisible battle against the laws of physics. So today, we're going to pull back the curtain and see how engineers make that invisible world visible. I mean, seriously, have you ever been driving over a huge bridge and had that little thought in the back of your mind? Like, what is actually holding all this up right now? It feels like it should be magic, but it's not. It is pure, brilliant engineering, all based on understanding the secret forces hidden deep inside the structure itself.
See, the real secret is all about what's happening inside. Down at the molecular level of every single beam, every piece of that structure, there is this constant, invisible tug-of-war happening, a hidden battle that decides whether the whole thing stands proud or, well, comes crashing down.
And this battle really boils down to two main players. On one side, you've got tension. That's a pulling force, kind of like a tug-of-war rope, trying to stretch something apart. And on the other side, you've got compression. That's a squeezing force, trying to crush something, push it together. Literally every part of a structure is either being stretched or squeezed.
So how in the world do engineers measure this fight? It's not like you can just look at a steel beam and see the stress, right? Nope. Instead, they rely on two classic, really powerful methods to figure all this out. Think of them as calling in two different kinds of specialists for two different jobs.
So, first up, we've got the detective. This approach is careful, it's patient, and it is incredibly thorough. It's called the method of joints, and its whole deal is solving the entire mystery one single clue at a time.
So, what's the detective's game plan? They focus on the joints. All those points where the beams connect to each other. They go to each joint, one by one, and make sure that all the forces pushing and pulling on that single point cancel each other out perfectly. If every single connection point is in balance, well, the whole structure has to be stable, right?
In a process, it feels just like a real investigation. You find your easiest starting point, your first lead. Then you isolate that single joint, look at all the evidence, the forces acting on it, and solve for balance. Once you've cracked that joint, you use what you learned to move to the next one, and then the next, slowly building your case until the entire structure's secrets are revealed.
But here's the absolute golden rule for this method. You have to know where to start. You can't just dive in anywhere. A good detective starts where the case is simplest, at a joint that only has one or two unknown forces. That's your foothold. It's the clue that lets you start unraveling the whole puzzle.
And once you've done the math figuring out the clues, it's super straightforward. If your calculation gives you a positive number, that's your clue that the beam is being pulled on. It's in tension. If the number comes out negative, it's being squeezed. It's in compression. Simple as that. Case closed.
But what if you don't need to know the force in every single piece? What if you're really just worried about one specific critical spot? Well, for that, you don't need a detective to spend all that time on the case. No, for that, you call in the surgeon. Fast, precise, and gets right to the point.
See, the surgeon's approach is totally different. Instead of going from joint to joint, the method of sections involves making one clean, imaginary slice right through the guts of the structure. This cut exposes those hidden internal forces you care about, letting you solve for them directly. It's a surgical strike.
The procedure is exactly like a real operation. First, you identify your target, the beam you need to investigate. Then, you make one single, straight incision through the structure. You take one of the two pieces you just created, look at it as a whole, and you solve for its overall balance. And bam, just like that, you've found the force in that one specific beam you were curious about.
But, and this is a huge but, this whole technique hinges on one absolutely critical non-negotiable rule. The entire success of the operation depends on making the cut in exactly the right place.
And that's the magic number, 3. Your imaginary cut can only pass through, at most, 3 beams where you don't already know the forces. So why 3? Well, it's because in 2D analysis, you've only got 3 fundamental equations of balance to work with. If you cut through 4 or more unknowns, you'll have more variables than equations, and the math just breaks. The problem becomes unsolvable. The surgeon has to be precise.
Okay, so we've got the patient detective on one hand and the speedy surgeon on the other. They're both powerful, but they're built for totally different missions. So how do you know which one to call?
Well, it all boils down to your mission. If you need a complete picture, the forces in every single member of the structure, then you call the detective, the method of joints. It's slow, but it's thorough. But if you just need to know what's happening in 1 or 2 critical beams and you need that answer now, that's a job for the surgeon, the method of sections. It's a fast, targeted strike.
Okay, so we've got our methods. But the real end game here is to build an intuition, a gut feeling for this stuff. So for our last little challenge, let's throw the calculators out the window. No equations, no numbers. We're going to try and solve a structure just by looking at it.
Just look at this simple structure here. Based on everything we've talked about, can you guess which parts are getting squeezed and which are being stretched? Think you can do it? Let's walk through it together.
Okay, first things first. It always starts with the load. Let's just imagine a heavy weight is hanging right from the middle. That force is pushing straight down, and that's the force the structure has to fight.
And of course, for this thing not to just plummet to the ground, the supports on either end have to push back with an equal and opposite force. They're pushing up. That's Newton's third law right there, setting the stage for our invisible battle.
Now just follow that force. That upward push from the supports travels right into those angled outer beams, right? It's basically squeezing them from the bottom up against the load at the top. So right away, we know those outer members are in compression.
But at the same time, that squeezing force is trying to push the supports outwards, making the whole thing want to do the splits. So what's stopping it? It's that bottom beam. It's being pulled tight, like a rope, holding the two ends together. It's in tension.
And just like that, no math required, we can actually see the invisible battle. The outer pieces are squeezed in compression, while the inner piece is stretched in tension, and they're all working together in this perfect, elegant harmony. So, from now on, when you're looking at a bridge or a crane or even the rafters in your own attic, you'll know. You'll know about that hidden world of pushing and pulling that's holding it all together. The question I want to leave you with is, what other invisible forces can you spot at work in the world around you?